Good morning, everyone, and very welcome to the 2022 Crafoord Symposium in Astronomy, Solar Wind and Magnetic Fields in Space. My name is Dan Larhammar, and I'm the president of the Royal Swedish Academy of Sciences. I'm delighted to see you all here to celebrate the 2020 Crafoord Prize and the achievements of the Crafoord Laureate, the late Professor Eugene Parker. Before we enter the world of astronomy, let me tell you a little bit about the background of the Crafoord Prize and how it all started, the very reason that we can be here today and enjoy science and research at top-class level. The founder of the prize, Holger Crafoord, was a Swedish industrialist. He was born in Stockholm in 1908 and graduated from the Stockholm School of Economics. In the 1940s, he worked for a company here in Lund called Åkerlund and Rausing that manufactured packages. Holger Crafoord served as the managing director from 1946 and for more than 20 years. The company formed a subsidiary already in 1951 that was named Tetra Pak. This became a huge success with their clever cardboard packages for beverages like milk and juice, in the shape of a tetrahedron with a plastic cover on the inside. The success of the company meant that when Holger Crafoord sold his shares in Tetra Pak, he made a considerable profit. He was approached by a medical researcher, inventor, and professor who was devoted to improving treatments of his diabetes patients, suffering kidney patients. The researcher Nils Alvall had invented an artificial kidney a few years earlier to purify the blood of his patients. Holger Crafoord founded the company Gambro here in Lund in 1964 to develop and manufacture this device, and production started a few years later. This dialysis instrument and its followers have extended the lifespan and reduced the suffering of millions of patients. So Gambro 2 was a great success and went on to improve other things in medicine. It became an international company, and since 10 years it is owned by Baxter in Illinois. The success of Gambro made it possible for Holger Crafoord to set up a foundation for research in 1980. The foundation awards prizes in areas of research that are not covered by the Nobel Prizes. In addition to astronomy and mathematics, also in the geosciences, in the biosciences, especially ecology, and in polyarthritis, which is because Holger Crafoord himself suffered very badly from rheumatoid arthritis in the later part of his life. These prizes are awarded in a 4-year cycle. Holger Crafoord passed away in 1982, the very same year that the first Crafoord Prize was awarded in mathematics. So this year is a 40-year jubilee. Then let me just add a few words about the Laureate selection process. This is handled by us in the Academy of Sciences, and we receive over 100 nominations each year. We have an extremely careful selection process, evaluation by a prize committee, very similar to the Nobel Prize committees, and the decision is taken in the Academy as a whole. This is one of several important tasks of the Academy of Sciences, all of which aim to promote the sciences and strengthen their influence in society. Another way to do this is to provide meeting opportunities for scientists, like we are doing here today. In 2020, the Crafoord Prize was awarded in astronomy and mathematics, and finally, the prize ceremony and the corresponding symposium are taking place this year. Now, sadly, the Crafoord Laureate, Professor Eugene Parker, is no longer with us, which we deeply regret. He passed away just over a month ago at the age of 94. To commemorate him and acknowledge his important contributions, I propose we pay tribute by a moment of silence. Please raise. Thank you. I will now give the word to Jan-Erik Wahlund, who is a member of the Crafoord Prize Committee in Astronomy and a member of the Academy of Sciences. So I wish you all a very rewarding symposium. Jan-Erik, please.
Thank you. Crafoord Laureates, President of the Academy of Sciences, Swedish, and the Crafoord Foundation, ladies and gentlemen. So let me introduce the 2020 Crafoord Laureate in Astronomy, Eugene Newman Parker, with the motivation for pioneering and fundamental studies of the solar wind and magnetic fields from stellar to galactic scales. He got the medal and the honor and the credits for his life work a year ago. So he have felt the honor of the community and had everything to be proud of. I will only do a short introduction. I have 5 minutes. So of his work, and we will have a very great symposium here with distinguished speakers. Okay, see if this works. So his first achievement, I will say, is to find the theoretical foundation of the solar wind, and this is imaging by the Parker Solar Probe. And the Parker Solar Probe is named after him. And you can see the streaming of the solar wind coming out from, it's the corona that is very hot. So you have a photosphere which is around 6,000 degrees, but then something is heating it, still not exactly known today what it is, but this heating causes the solar wind to expand into the planetary system. It's a plasma and it has a magnetic field. And what Parker did was that he found the dynamic theory for this plasma and how it evolves from the sun. In this paper already in 1958. And it's interesting, one can read here in detail, just a few first sentences. We consider the dynamical consequences of Biermann's suggestion. He had looked at cometary tails and seen that they are always propagating from the sun, implicating that there is some kind of wind from the sun, and it's not a static body at all. But what Parker did was that he put in detail the dynamic theory, MHD, magnetohydrodynamic, into this concept. Often streaming outward in all directions from the sun with velocities of the order of 500 to 1500 kilometers per second. These velocities, 500 kilometers per second and more, and the interplanetary densities, etc., is still holding to the day. Here's another view. This is from the stereo spacecraft, I think, and you can clearly see the involvement here. And you can see Eugene Parker here looking at the streamer, I think these are called. And it has later on been very much verified that his theory is correct. He have done much more than that. There are not only the mechanism for the solar wind. The solar wind is going radially outward from the sun, but then the sun rotates and the magnetic field is kind of twisting into a spiral, and we all today call this the Parker spiral, which you see here, and it is this wind and the magnetic field that is going supersonically outward from the sun and hits all the planets and bodies in the solar system. And this gives rise to interesting interactions with the magnetosphere and ionospheres and other bodies. He also, in 1961, you had this wind coming from the sun, and he then realized this wind will slow down and become subsonic after a while. And then you will have a termination, and it will form a kind of enclosement around the sun, which we today call the heliosphere. And it also hits by the interstellar winds. And this drags out probably into a tail, and we will hear more details during the symposium today, I'm sure. So this is another very good achievement, which here came to in 1961. He has also done more than that. He have worked with cosmic rays from the sun and also in the galaxy. He have also done big achievements in solar and also stellar and galactic magnetic fields. And it includes also plasma. This is not really related, but you can almost see this is the Helix Nebula taken by the Hubble Space Telescope. You can almost see a wind coming in. This is the interstellar wind, and you can see these bubbles in space, which one can call heliospheres of various stars. And he later come with 1973 with the extragalactic cosmic rays and the galactic magnetic field paper, describing how magnetic fields are created near stars and in the galaxy of our galaxy. There are many papers. This is only an examples of them. Many of these papers are having him as a single author. Many of these papers have over 1,000 citations. I think there's very few that have a single paper with 1,000 citations. He has many, many. And that marks his legacy for space sciences, I think. I marked in bold one of what I think is the more important one, hydrodynamic dynamo models, 1955. And then I have shown you these three. Also, I find dynamical theory of the solar wind, 1965. Fantastic paper. Anyway, let's have a great day. Let's have a great symposium. And to the honor of Eugene Parker. Thank you. You, Axel Brandenburg, as the chairman, and you take over, I think.
Is this on? Is this on? Ladies and gentlemen, it's a great pleasure to welcome you all. I've seen the variety of topics that Eugene Parker has been working on. This is now reflected in the variety of different topics that we will be hearing about today. The first speaker is one of Gene's early students in the field. He did his PhD at the University of Chicago in 1973. He then moved on to Boulder, Colorado, where he has been working first as a postdoc and then as a senior scientist at the National Center for Atmospheric Research and the High Altitude Observatory. So with that, I give the word to Boon Chye. It's a pleasure to see you again, Boon Chye, and he will be talking today about the coronal heating by topological dissipation of magnetic energy, one of Gene Parker's very important subjects. Boon Chye, please. Take it up.
Thank you, Axel. I hope everybody can hear me clearly. I'm here today as a presenter. I wish to thank the Royal Swedish Academy of Sciences as well as the Crafoord Foundation for inviting me to speak on behalf of Professor Gene Parker. And I should say something that is very personal. Gene was my teacher and a dear friend for more than 50 years. So with that personal note and thoughts of him, I joined the Crafoord celebration of Gene Parker today. The theory of coronal heating, there's several different theories, but the one that Gene Parker worked very hard on, largely because he actually saw something fundamental in the problem. So let me do it in the following way. So here's the picture of the coronal heating process that Gene Parker saw, and it centers upon what he called the fundamental magnetostatic theorem that he discovered in 1972. It has to do with the corona being so highly conducting, and most remarkably enough, it's highly conducting, then one would assume it is not very resistive, but it is very resistive for dynamical reasons. So the way to look at it would be to look at the Lundquist number, which compares the time scale for resistive dissipation and the time scale of the dynamics of, say, a solar phenomenon. And one finds that that time scale is so disparate, the two time scales are so disparate of the order of 10 to the 10 in the case for corona. And the reason magnetostatic equilibrium is important here is that Gene discovered when a magnetic field, especially one in 3D chaotic topology, attains equilibrium, it invariably or inevitably forms current sheets. And the sheets thin down to an unlimited thinness, that the reason for its forming being near perfect conductivity begins to break down because the thickness of the sheet goes to the zero. Excuse me. Whereupon then the sheet dissipates. And once the sheet dissipates, the high Lundquist number environment returns and current sheets form again. And in this sense, the corona is not really in equilibrium. It is in an endless non-equilibrium, maintaining large-scale force balance, but heated on the small scales by all over the place, ubiquitous, intermittent, resistive dissipation of current sheets. The energy is provided by the magnetic field in the corona, and that part is the easy part of the theory because the heavy, slow-moving fluid, turbulent fluid beneath the corona generates magnetic energy in the form of a flux of energy, the Poynting flux that replenishes whatever free energies that's liberated by the heating. So here are the different components of the heated corona. And we have this remarkable view of the corona that at 1,000,000 degree temperature, of course, is fully ionized and therefore highly conducting. But the near perfect conductivity is as much a consequence as it is the reason for the corona's high temperature. So today's talk is going to focus on sort of, looking at the theory of MHD. So we're going to focus on the elements of the magnetostatic theorem, first discovered in 1972 by Gene Parker in a paper in the Astrophysical Journal. And that led to a lot of work he did, and those works were summarized in this monograph published in 1994. in 2010, he came to visit us with Mrs. Parker and with a very bright postdoctoral fellow from Oslo, also married Janse. We wrote a paper that gave us another sort of a look at the theory, and that's where we are going to take off from. So the lecture is going to follow Jim Parker's analysis that led to his theoretical discovery that the magnetically heated corona is not just something of the sun, it is a universal phenomenon. So I'm going to run through a number of slides to sort of review the different components of this theory. So we should, of course, start with what we see of the sun. And nowadays, we have data coming in from the sun every day. So here you have the sun on July 3rd, 2020, the photosphere, that is the white light surface of the sun, where 10 to the 33 ergs per second energy go clear through the upper atmosphere, which is optically thin. And the temperature is about 6,000 degrees. And it is the magnetic field that makes the sun so interesting, especially in the corona. So the second image here, let's see, I have a pointer, here it is. The second image here shows the blotches of black and white, the polarity of the line of sight magnetic field that we can observe directly and map over the solar surface. And you see very concentration of pairs of positive and negative magnetic polarities, and those corresponds to the sunspots. But once we go above the surface of the sun through a very thin layer, something like 1 part in 100 or so of the solar radius, then we see the million degree temperature of the sun. And this image here at 1.5 million degrees is rotated in this video to show you that the structures that you see, they're long-lived, and you see it across a huge range of temperature. You see good correspondence between the 1.5 million degree temperature and the 3 million degree temperature on the right, observed or imaged by these. This is pretty hard X-ray instrument of the Japanese Hinode satellite. And what we're after today are these flickering that you can see all over the sun, and those are reasonably interpreted to be magnetic reconnections, and it's all over the sun. So I emphasize the slow motion on the surface of the sun, 0.5 kilometers per second. It's very slow compared to the Alfvénic timescale in the sun, about 500 kilometers per second, and the sun's corona sort of evolves quasi-statically, but at the same time, all over the place, heated by a process. Okay. And before I proceed further, I should also remind ourselves that humankind actually knew something of the sun, the corona, and they saw it with their naked eyes since prehistoric times. I have a typo here. So the white light sun is the corona seen in the scattered light, the scattered white light from the photosphere, and the scatterers are the free electrons in the corona. So the large-scale magnetic field orders the large-scale corona into units of 3-part structures. These are the coronal helmet streamers, long lanes of closed magnetic fields closer to the sun where the field dominates, and then further out, the inertia of the solar wind expanding in all directions drags the field into its open configuration. And the helmet itself has a 3-part structure: the streamer, the dense shell of the helmet, and then the cavity. And those are fascinating things. But the point that I really want to make here are two. The first is that this is a very unusual eclipse. The coronal mass ejection, one of these 3-part structures will blow out. What's going on during the few minutes of a full eclipse, and that was observed in space by a coronagraph. The occulting disk of the coronagraph is about twice the radius of the sun, and that's just to remind ourselves that the quasi-static corona that I'm going to describe is only the general background of the corona, whereas very active events like the CMEs and the solar flares would interrupt this long process of the corona existing as a quasi-static system. How do we describe the corona? The zeroth order, the simplest description that where you must start, will be a fluid description, and it's just Newtonian mechanics. So you have fluid, this is the acceleration term, the velocity and the density, and the magnetic field with high conductivity together with the current gives you the electromotive force, which is your Lorentz force. Then there's gravity, then there's pressure gradient, and there's viscous effects coming from the fluid itself. Then there's mass conservation, and then there's entropy that has to be accounted for with the source. And I put a red arrow there to remind ourselves that the corona is immensely complicated. And in this simple description, one has a convenience of saying there is a source of entropy, and it covers various things: thermal conduction, viscous heating, resistive heating, and so on, as well as non-LTE radiative transfer. And then finally, there is Faraday's induction equation that describes how the magnetic field is changed by an electric motive force. This is your induction here, and then there's a resistivity coming in that would destroy the current in terms of the diffusion of the magnetic field. So this is a picture that we have of the corona. In the corona, the magnetic field dominates. So the ratio of the gas pressure to magnetic pressure is very, very small. And the Lundquist number is so large, so implying that the resistivity, which is not zero, but is almost negligible until you get to very thin or small scales. So to make Jim Parker's point about the magnetostatic theorem, let's take the extreme case of this system. Namely, we set beta to 0, pressure is not important, and we set eta, the resistivity coefficient, to 0. Then we end up with a more manageable theoretical problem to solve. Namely, we're looking at a magnetic field that drives the flow with this Lorentz force, that's your magnetic force, and we keep viscosity, which is actually even weaker than resistivity. But we're keeping this thing here for a very important theoretical purpose, which is to demonstrate the point that Jim Parker has in his magnetostatic theorem. Then there's mass conservation, and here you have Maxwell's equation or Faraday's induction equation without the resistivity, okay? Now, in textbooks, we often celebrate the Eulerian description of fluid mechanics. Namely, it is wonderful just simply to be bothered only about with quantities, velocities, magnetic fields, where it is at a space-time point without worrying where each particle of fluid has gone. That's your Eulerian description. But if we describe it in terms of Lagrangian description, meaning we are interested in following each piece of fluid as it moves around, that is really closer to a physics thinking brain. So here we are, equivalent to the Faraday induction equation. We could describe that same process in terms of fluid surfaces. Then that induction equation says that the magnetic flux, the amount of field of magnetic flux threading through it, is constant as you follow the fluid surface around. Now, fluid surface could also be a flux surface, meaning it coincides with the magnetic flux surface, meaning the field lines are all tangential on it. And from this simple theorem, two things comes true. The flux surfaces behave as fluid surface because the same fluid is always stuck on it, which also means the two flux surfaces, as it moves, contains exactly the same fluid between them. And therefore, we begin to think of magnetic, in this particular class of MHD problem. Here is a flux surface sketched by Jim Parker, which is rather corrugated and complex. But these flux surfaces between themselves partition the fluids into invariant fluid volumes that you can follow around, almost like just a volume of fluid, or even like solid particles moving around just following each one of them. Okay, and there you have something that we better keep in mind with high conductivity, because these partitions are permanent. So we are really looking at flux tubes moving around with integrity, each tube containing the same fluid. And when they push themselves around in the three-dimensional freedom of unrestrained space, it's very easy for two flux tubes to push their way and come into contact. And that in that process, you're going to discover that the magnetic field creates tangential discontinuities across the magnetic flux surfaces. And therefore, the magnetic field is actually not continuous. And where it is not continuous, there are sheet currents flowing on the surfaces separating with these tubes. So one thing I must start off by emphasizing is that once you talk about highly conducting plasma, creating very thin sheets of current is actually the hallmark of the idea that this is so perfectly conducting. And so if we were to go back to the first statement I made about what the corona is doing, that when you try to the magnetic field in this process of finding forced balance, current sheets such as I've described is actually a very natural consequence of it. But what makes it so interesting in the corona is that it is not a perfect conductor rigorously. Resistivity is small but finite. So at some point, the large Lundquist condition, large number Lundquist number condition breaks down, and then reconnection would then take place. Okay, so that is a picture that we're going to have. Now, the problem that Jim Parker formulated was this: we take the perfectly conducting fluid and let's do an initial value problem. So we think of the bipolar magnetic field in the corona as ropes of magnetic fields with field lines woven into some chaotic fashion, all very tangled up by the heavy fluids down below the base of the corona. And to do that problem for a theoretically convenient way without having to deal with this realistic geometry, you should think of the field as anchored between two parallel plates. And we start off with a uniform field threading through the two plates, and then by relaxing the rigidity of one plate and moving the foot points round and round in some chaotic fashion, and then refreeze them, we create out of the uniform field a highly tangled field. And by choosing the displacement of the foot points to be incompressible, then we don't change the original boundary condition of the flux being uniformly threading through the two plates. And here we then pose the problem for the initial value problem that is so instructive. So we start off by saying that, well, you start up at time you go to zero, the density isn't so terribly important except for the fact that it's frozen into the field. So we set it to a constant, and the velocity is zero, so it's a static initial condition. And we start off with the initial field, which corresponds to this bunch of tangled field lines. And it is always described in terms of a departure, not necessarily small, but a departure from the uniform field. And then down at the plates, we have rigid boundary conditions, meaning at the plates, because the fluid is frozen into the field and the field cannot move at the surface, the velocity is zero at both plates during the subsequent evolution of the system. And then you have some boundary condition far away, because this is an infinite system, in the direction parallel to the plates. So things should be well behaved at infinity. And for this problem, you have a simple energy theorem. It says that the total energy above the uniform magnetic field and the fluid's kinetic energy, if you sum them together, that total energy will always would decrease monotonically with time. And that's hardly surprising. The Lorentz force, which is pushing the fluid, generates kinetic energy. and the kinetic energy simply just dissipate away by viscosity. And eventually, the total energy being finite must go to a constant, and the rate of change of the total energy has to go to zero, and therefore the velocity has to go to zero. Whereupon, then we see that you have a magnetic field which is force-free, meaning that there is still current flowing in there, and the force is everywhere zero. In other words, the magnetic force is self-balancing. And if you wish to know the end state, you simply have to solve this equation written down here within the blue color brackets. Now, this equation is too simple. It has got an infinity of solution. It doesn't define any specific solution, but we have forgotten that we are doing an initial value problem. So we should go back to say, well, there was an initial magnetic field in there. And therefore, out of the infinity of solutions you're going to get out of the system, you only need to find the one that can be justifiably identified with the initial magnetic field. And if you could do that, that's how you pick out of the infinity of solution, the relevant solution that is the proper solution to the initial value problem. And if we follow the classical way of learning physics with mathematical equation, we think of analyticity. We assume these equations assumes analyticity, and therefore we expect the end state to be an analytical solution of the force-free equation. But having gone through my previous slide to say that current sheets are naturally formed as a hallmark of a perfectly conducting fluid, then we must allow for this end state to also contain current sheets. And this is where the magnetostatic problem tells us, a theorem tells us that in fact, the discontinuous solutions is the rule rather than the exception. And that's where I'm going to see if I can really finish in time to show you the most exciting part of how this actually makes a lot of sense once you understood what the theorem is saying. But first, some intuitive feeling for how a perfectly conducting fluid behaves. So here is an example, and it is a two-dimensional example. And it's two-dimensional, so that it's easy for us to figure out how it really works. So in the XY plane, we imagine there are three magnetic fluxes, the two shaded ones kept apart by the overlying unshaded magnetic field that pushes down and keep the two shaded lobes of magnetic field separate from each other. And this solution is a potential for solution. So it is a potential field, and so it is a force-free magnetic field. But if I were to take the boundary and move the 4 points and squeeze them towards each other, as indicated here by how this 4 point P has gone over here and Q has gone over here, then the topology doesn't change. That means the connectivity doesn't change, but the field is now no longer in equilibrium and would attempt by frictional relaxation to reach an equilibrium. And in the case of the magnetic field in a 2D plane, the current is always perpendicular to the field. So if it is force-free, meaning that the current is parallel to the field, then the only way you can have that would be for the current to be zero. And that potential field corresponding to the newly displaced foot points of the foot point actually carries a neutral point, and therefore is not a state available to this field. And that is the reason that as the two lobes of shaded fields crush towards each other, they meet and then they form a discontinuity, and that is your current sheet. But once this example is accepted, your imagination simply tells you, you know, you really got to think of similar processes difficult to treat intuitively as I've just done so for the 2D field, namely that three fluxes as shown on the right-hand side can actually push themselves together, and the maroon color flux surface and the white flux surface push themselves so hard together that a hole is actually made in the flux surface colored green. And where they meet, there will be a tangential discontinuity. And that is a process we are interested in. And so how do we go about making some sense of it? I need to pause for a minute and talk about field topology. So if I were to come down to the tangled field, there is a sense that the field is tangled and also frozen into the fluid. There's no way for these field lines or flux tubes represented by these field lines to pull apart from each other. I'm looking at my clock to see where I am. Okay. And it's very difficult to describe topology. So we're going to circumnavigate around it and say that topology is actually rather simple if we talk in terms of topologically equivalent geometrical objects. So if you can't cut and reglue, then as you deform geometric objects, then two objects can be said to be topologically equivalent if you could deform one into the other, and it's a reversible process. So if we just talk about topologically equivalent objects, then we don't have to deal with the showstopper of having to deal with how to calculate that. Then in the Parker problem, it turns out that your initial magnetic field is not just the specification of an initial condition. That magnetic field with its foot points anchored to the two plates defines the topology. And therefore, it is just a simple physical state of a magnetic field whose topology cannot change as long as it's anchored between the two plates. And so the Lorentz force that drives an initial field of a fixed topology is actually driving the evolution through all the states of topologically the equivalent fields to a unique state. And that unique state is what that equation for the force-free field we were setting out to calculate. And now comes a very interesting question. We thought of these fields being continuous and smooth and evolving towards a final state. There is a non-trivial question. The evolution could be very smooth, but is the terminal state, the B subscript infinity, necessarily be continuous and resides in the same space of continuous field? And this question brings us to the threshold of the magnetostatic theorem. So this part gets mathematical, but I think it's so crucial to be able to sort of come to grip with it. You see, the force-free, the Lorentz forces make up of two components. One is the tension force, that's the first term here, and that tension force acts in a direction perpendicular to the tangent to your field line along its normal. So it lies in the plane of your circle of curvature and the tangent. Whereas the pressure force is always acting perpendicular to a surface of constant pressure. So under these conditions, you have to worry about how compatible could the two forces that are geometrically so different be made compatible. And when you say it is force-free, you're asking for these two geometrically very different forces to equate. And let's see, let's see what can I say about expecting the field to be analytical. You see, if you set the Lorentz force to 0, this magnetic pressure force obeys a very simple rule, which is analytical. It says that there is this identity in vector calculus and it's automatically 0. So if we take the curl of this tension force, you come up with this corresponding condition for the tension force. And only if you satisfy this necessary condition would you expect the solution of the magnetic field to be continuous, and in which case you solve this very nice looking force-free equation setting your current density parallel to the magnetic field. When Eugene started with this problem in 1972, he faces terribly difficult problem of solving these, multi-dimensional problems, but he came on something very ingenious, very original. He simply asked himself if this condition here, let me go back again. I'm using Zoom for the first time, so please excuse my clumsiness here. Now this condition here, he said, let me start with that. This is a condition I must satisfy, and this is a condition on the tension force. So to deal with that, he looked at a simple way of solving the force-free equation. He looked at a magnetic field that can be expanded as an infinite series in a small parameter epsilon. You might think of the epsilon being the tiny little cells that twist the magnetic fields into the highly braided structure. And when you do that, your boundary conditions, you must maintain that the surface flux coming through the two plates is uniform as the, consistent with the way this force-free field has been created. Then when you apply the condition, the necessary condition for your magnetic field to be analytical, then it comes, you can work your way all the way through to show that such a magnetic field cannot vary with height. But your initial field, the way you twist it around, is unrestrained. So this is an absolutely restrictive condition for all force-free field, at least in the expansion of your epsilon, to describe it. And so he drew this very important conclusion, and I'm going to read. This came from his book. All but the simplest prescribed magnetic field initially must evolve into a minimum energy force-free terminal field, not everywhere continuous, and embedding infinitesimally thin current sheets on pieces of magnetic flux surfaces. And if that were the case for the majority of the initial states for the magnetic field, you will have to solve an awesome force-free equation where Ampere's law, which describes the current density, is not only everywhere locally to magnetic fields, but it runs into discrete currents where there are tangential discontinuities in the magnetic fields where sheet currents flow, and those sheet currents too also have to be in equilibrium. But what he was thinking of is he has pretty much gotten to a very, very important conclusion. See, here, if you have been discouraged by my mathematics, let me talk on conceptual terms. And this really is very beautiful. What the theorem based on the epsilon expansion is telling us is all the topologies you can have between the two plates can be decomposed into two complementary subspaces of topologies. One of them contains topologies such that the field with those topologies can evolve into an analytical smooth magnetic field with no current sheets. And in the case of corona, these guys can't deliver any heating with resistive dissipation. And then there's this other space where every one of these magnetic fields will evolve into a force-free field with current sheets. And because the corona's resistivity is not zero, but only very small, these sheets will dissipate. And because it's so restrictive to have a analytical smooth current force-free field, it follows that the set of magnetic fields forming current sheets because of its topology is in the sense so much larger than the set of magnetic fields that is that are compatible with a terminal state which is smooth and analytical. And the way to look at that would be, if you were to look at all the topologies possible, then those that can relax to a smooth magnetic field is so small that if you pick any one topology, the chances of you landing on a smooth magnetic field is, in terms of probability, is 0. And there, you know, I'm running out of time. I'm sort of concerned. Now, but let me cut to the chase of this whole thing. If in the corona, based on this theorem, one has to conclude that any equilibrium available to it in the force-free state, it is very, very improbable for that system to find a state which is smooth, which simply means that current sheets will form. And if the corona is perfectly conducting, then that will only mean nothing more than a very unheated atmosphere creating current sheets that don't dissipate. But the corona's resistivity is finite and small, and therefore it would dissipate. But upon dissipation, it has to find new equilibrium. But since the probability for any magnetic field to relax to a smooth force-free field is, in terms of probability, you know, it's 0 probability. And that's crucial. That simply means this magnetic field in the corona will never find any equilibrium, meaning that it's plagued with current sheet dissipation, and there emerges the picture that the corona magnetic field achieve equilibrium only on the larger scale, and it would behave, you know, it would evolve quasi-statically, but it cannot avoid a pervasive reconnection that's going on in the small scale. But here, I have to come back to remind ourselves that for simplicity, we have assumed that the two plates were rigid so that we can deal with how the magnetic field by the viscous relaxation will arrive at a terminal force-free state. But of course, there a very important point comes through. The rigid boundary implies that your magnetic field has a finite free energy. And that would simply just decrease in time. And eventually it will come to a state with no more energy to release. But a key point of this theorem is saying that even that relaxation is not going to do a simple relaxation to a smooth magnetic field in the corona. It will simply keep forming current sheets. The fact that your free energy is finite only means it will form current sheets inevitably, but of a diminishing intensity. And therefore, it also approaches a very quiet end state in the end by repeatedly forming current sheets. Now, in the real corona, the heavy fluid below the corona drives the system, and it replenishes the magnetic energy, and therefore the level of resistive reconnection that is going on a small scale that pervades all over the corona is then sustained. And that is the way the corona goes about remaining heated to its million-degree temperature. And I'm still looking at my clock. So this theorem does a lot more than that. If we believe that the conclusion, or we accept the conclusion that there's sort of an immensely larger part of the topology space where every field must form a current sheet, and it's such a small space where the field is analytical, then the analytical field is actually distributed in a very densely populated space of all the different topologies. And that is the reason why once reconnection starts, and new topology forms after the reconnection, it simply just stays in this larger domain of densely populated fields that forms current sheets. And to prove Jean's theorem with generality, we have something we can exploit, which he does so beautifully in his book. Namely, if you look at a smooth analytical force-free magnetic field, that state is embedded in the neighborhood around of it are all the current sheet bearing force-free field. And so with that as a hindsight from the magnetostatic theorem, if you were to take that equilibrium, analytical smooth equilibrium, and give it a nudge, you will be able to find how the field has to evolve current sheets. And so I would like to conclude this lecture with a very interesting example that Jim Parker and I sort of discovered almost at the end of our discussion. So let me quickly go through that. I think I'm running out. I've got only 4 minutes left. Mr. Chairman, what shall I do? Shall I just
explain and then come to the conclusions? Thank you.
Okay, so this is a very interesting twist to the problem. So there's a well-known force-free magnetic field discovered by Lundquist that all of us who work in MHD always learn first about Lundquist force-free field. So what is a Lundquist force-free field? It is a field which has radial symmetry. Everything depends on the radial coordinates in cylindrical geometry. And it has got a z component and an azimuthal component. And this is the z component. It goes through a reversal as you go out. And then the azimuthal component goes to a maximum and comes back down. And it is force-free because the tension force and the magnetic pressure force balance perfectly. So if we were to modify Lundquist field by removing the z component altogether and replace it with a uniform field, then we have a Parker non-force-free modification of the field. In other words, we take the azimuthal field as it is, but the axial field is a uniform field that extends out to a uniform field outside, and ask ourselves, if that were the initial field, what would the initial value tell us the end state would be? And that is shown very quickly in this picture. So on the left-hand side here is the plane through the cylinder, and there's the axis of the cylinder, and these lines here, this is a transition where the Lorentz force pushing the fluid is inward, like in the pinch effect, and on the other side, it is outward. And this is a boundary with the potential, with the uniform field on the exterior. The inward pushing Lorentz force give rise to what is well known as a pinch effect. The tube constrict, and the Lorentz force pushing it outward will push the boundary out into the uniform field outside. But what seems so remarkable about this field is the following. The pinch effect, there's a paper Jim Parker showed that a pinch effect of this kind with the field anchored at the end is diverging as you go to the boundary where the field is held rigidly. Then all the twists will propagate to the open end of it. On the other hand, on the external layer, the twist will propagate to the equatorial region, so that towards the base here at the two ends, the field is azimuthal, more azimuthal than axial, whereas on outside it's more axial than in the equatorial region where the field is azimuthal. And this then is a very natural place where a current sheet is going to form. So I have something blocking my view of this picture on the left. But this example makes a very interesting point. You start off with a very simple modification of a Lundquist field, where the axial field that had held the azimuthal field in a force-free equilibrium is removed and replaced by a uniform field. And in the simple modification, it simply evolves through such a remarkable interaction between the field that goes through a pinch at the axial axis and the field that pushes outward, and the current sheet forms right in the interior, as well as at the outer boundary where it meets the uniform field.
Boon, it would be good to have a bit of time for questions.
Yes, I am at the last slide. Well, I apologize for rushing it through this way, but I guess I had a hard time trying to think of how much can I put this in the talk. But this is really how remarkable this theorem is. So I thought a good way to conclude is this: to give you a quote from the monograph that Eugene wrote. And what he said was, this is taken from a sentence. He said he found it a remarkable result that any but the simplest field topologies had no equilibrium, because the field is in a state of non-equilibrium, that is rapid reconnection, and I add, never returning into any part where the field could be smooth, because there's just not enough significant space where you could get in there. And this is true if it has any but the simplest topologies. And as a presenter, I thought I should make the concluding thought. So Eugene's discovery, as is true of many of his work, is as much about a fundamental MHD property and process, the theorem, as it is about the nature of magnetic heating of the corona as a universal astrophysical phenomenon. And it is a universal phenomenon. Stars and galaxies have X-ray emitting million-degree coronae that must also be expected to be expanding into stellar and galactic winds as a compelling way of thinking about universality and consistency, or what physics can know. So I thank you for following me through up to this point.
Thank you very much, Boon, for a very interesting talk.
Thank you.